I'm Ms. Wu. Let's look at types of stationary points. So a stationary point is a point on the graph where the gradient is 0. So when you draw a tangent, it looks like this. Not positive, not negative, 0. There are three types. There's a local minimum, a local maximum, and these two we've seen before, and we call them the turning points of a parabola. And there's also a stationary point of inflection. Now local minimum looks like this. That's a local maximum, and that's a point of inflection, and so is that one. So we notice that the gradient is 0 at those points, but right before it we see that the negative is negative for that one, and right after it's positive. Whereas for a local maximum, right before it it's positive, and right after it's negative. Whereas for points of inflections, before and after they're either both positive or both negative, so going down. Recap, so the gradient for a local minimum goes from negative to 0 to positive. For maximum goes from positive to 0 to negative, and for stationary point of inflection it stays the same on both sides. And we can describe it by saying the function is strictly decreasing immediately to the left and strictly increasing to the right of a local minimum. The function is strictly increasing immediately to the left and strictly decreasing to the right of a function at a local maximum. And we can say that it is strictly both decreasing to the left and right or increasing to the left and right of a point of inflection. Let's do an example. Name the types of stationary points. We can see that here we have 3 points which are stationary points. Let's call them ABC. Now the first one is a local minimum. That one is a point of inflection, and that one is a local maximum. We call them local because even though in this area here, this is the maximum, but if you look at the whole graph, there's a value bigger than that. So that's not the total maximum, it's a local maximum. Likewise, the local minimum, because in this local area, that's the smallest value. But if you keep looking at the graph, there's a value that's more negative than that value there. Example. Let's do another example. Sketch the graph of the function f of x equals x cubed minus 3x squared plus 4, labeling all intercepts and stationary points. So for the y-intercept, we let x equal 0. We've done this so many times, so we can see that's going to be 4. For the x-intercept, we let y equal 0. So 0 equals all of that. So how do you find the first factor? Use the factor theorem. What values can you put in to give you a remainder of 0? Minus 1. So x plus 1 is a factor. What do? You do long division. So x times what is x cubed? That's x squared. And then x squared times that, we have a remainder of minus 3x squared minus x squared is minus 4x squared. So then we have minus 4x. And then that's a remainder of etc, etc. So do that with long division. Now we have the quotient over there, so we have that factorized as x plus 1 and the quotient. Now can you do anything with that part? Yes you can. That's just x minus 2 squared. So now we've factorized it, we can find the x-intercept as minus 1 and 2. I'm going to write the x-intercepts and the y-intercept up there. Now let's look for the stationary points. So when the gradient is 0, so let's find what the gradient is. So bring the 3 down, we have 3x, 3 minus 1 is 2, and then 3 times 2 is 6, so minus 6x. So 3x squared minus 6x is the derivative of that. Now we have to let it equal to 0 to find the stationary point. So 0 equals 3x squared minus 6x. You can take the x out and the 3 out as a common factor. We have 3x equals x minus 2. So now x is equal to 0 or 2. So we have two stationary points. How do we determine what they are? Well, first of all, we have to figure out what the y values for these are. So to find the y value, we're going to plug into the original equation. So f of 0 gives me 4 and f of 2 gives me 0. It just happens to be 0. So we have two coordinates for the two stationary points, and now we're going to figure out what they are. So you're going to do a table and you're going to put your x values for, we're going to look at 0 first, the 0, 4. So you're going to put the 0 over there and you're going to write down what the gradient is at that point, which is 0. And that is the shape, or the shape at that point. Then we're going to go slightly to the left and slightly to the right and see what it looks like. So slightly to the left could be any value like -1, and slightly to the right could be 1. Now we find the gradient of -1. So using the gradient equation of -1 gives us 9, which is positive. And using the gradient equation to find what the gradient is at 1, we can see that the gradient right after is negative. So we can see that it's a local maximum. We're going to do the same for 2, 0. So the x is 2. But since we have 1 there, we're just going to add on to this instead of doing another 3. So if we have 2 as 0, right before it we know that it's negative. We have to find right after what it looks like. So let's do 3. So the gradient at 3, let's plug it in, we obtain 9. So if we obtain 9, that's positive. So it looks like it is a local minimum. So doing this table gives you shows you whether it's a local maximum, local minimum, or point of inflection. So how do we answer this question? Let's recap really quickly. First of all, we had to find x and y intercepts. That's one thing that you already know how to do. Then to define the stationary points, we had to derive the equation, let it equal to 0, find what the x values are, plug into the original equation to find the y values. Then we obtained the stationary points. And to determine the type of stationary points, we drew a table of the x values to the left and the right of each point, the gradient of those points, and drawing the shape, it is clear that we can see what type of stationary points they are. So let's sketch this. So I've just brought the information of their local max at 0, 4 and local minimum at 2, 0. So the 3 points, 0, 4, 2, 0, and then all the intercepts are there. So we know that 2, 0 is a local minimum, so we know the graph is going to do that. We know 0, 4 is going to do like a local maximum. -1 is just an intercept, so it's going to go through and do that. And double check that's a positive graph, so it looks correct. Last example, and we're going to use the CAS for this one. Sketch the graph of the function f of x equals -2 x to the power 4 minus 8x cubed plus 32x plus 32. So how do we do that? To find the x and y intercepts, let's bring out our CAS. Okay, so let's type the expression, the -2x to the power 4 minus 8x cubed and plus 32x plus 32. Now that we have the expression, we can do lots of things. For example, we can do shift comma to bring out the bar, and we'll let x equals 0 to find our y-intercept, which is pretty obvious that it's 32, but I just wanted to show the shift comma function one more time so you get used to it. If you go to action, advance, solve, and drag your expression, notice that I'm not retyping anymore. That will be the faster way to do your SACs or test. Make sure that the 32 doesn't get cut off, double check, hit enter. That will give me my x-intercept. So when you solve it, you obtain your x-intercept of -2 and 2. Let me write that down. So y-intercept and x-intercept. How about the stationary point? How do we do the stationary point? So for the stationary point, we have to use the differentiation function. The stationary point is when f dash x is equal to 0. So let's differentiate this. How do we do that? Let me zoom in so you can see. So you go to action, calculation, diff, and again, I'm just going to drag and drop that in, hit enter, and that is our derivative. Let's double check. So -2 times 4 is -8. The power of 4 take away 1 is power of 3. -8 times 3 is -24. The power of 3 minus 1 is 2. And then 32x becomes 32. So that's our derivative. Okay, next we have to solve the x values for the derivative. So what do? We take the solve function. We can go back to action, advanced solve, or we can just copy, drag and drop, and then hit the exe or enter button, and we can see that that's the x value at the stationary points. How do you find the y value at the stationary point? You would sub those values into the original equation. So that's a differentiated equation, that's the original equation. So let's grab the original equation and then hit shift comma again to get that bar, and then let x equals to -2. And the easiest way to do it is to highlight and drop it in there. Hit enter, that gives us 0. And then if I enter again, I get the same thing, but this time I want it to be equal to 1. So my other x-intercept, enter, and I have 54. So now I have the stationary points, the x values, and the y value. So I have -2, 0, and 1, and 54. So just quickly recap. To differentiate, you go to action, calculation, differentiate to get the derivative. So we derived it and we found the x values. Then we put into the calculators to find the y values, and we have -2, 0 as one stationary point and 154 as the other stationary point. And then we have to figure out what kind of stationary points they are by going a little bit to the left. So a little bit to the left of -2 would be -3, and then a little bit to the right, which to the right you could go -1, or I would just go 0 because it's easier. And then let's bring out our CADs again. Okay, so we have the gradient, and we need to find a gradient -3 to see what happens to the gradient slightly to the left. So hit shift comma to bring that bar. X is equal to -3. So it's 32. So the gradient is positive to the left of it. And now to the right of it, let's do 0. I'm just going to change -3, so highlight and then tap on 0, enter. So you don't have to type or drag anything again. And we obtain 32 again. So the gradient to the right is also positive. So that is a stationary point of inflection. And then we had another, let me turn the CADs off for a sec. We had another point over there, 154. So when x is 1, so we can have x is 1. We need to figure out, well, we have to the left. Now we have to figure out to the right a bit. So let's do 2. So let's bring out our CADs again and type in when x is 2, what is the gradient? So delete, hit 2, enter. It is -128. So -128 means that it is negative. So now we have a maximum turning point, local maximum. So at -2, 0, we have a point of inflection. At 154, we have a local maximum. That's all the information we obtained so far. Recap. So with the CAS in main, you can find the y-intercept and the x-intercept by typing the equation or the expression and going action solve for the y-intercept and shift comma to bring out the bar, x equals 0 for the x-intercept. And then we use the action differentiate function to find the derivative. But I'm going to show you in a second that you can also use the graph function, where you hit that button, and then if you hit analysis, there's so many things you can do under G-solve. You can find x and y values, then root means x-intercept, minimum means local minimum, maximum means local maximum. You have the y-intercept there, and you have the point of inflection. So let's bring out the CADs again, and let's try them. And I was to graph it by hitting that button up there. So drag and drop the original equation. Let's change the y maximum to, what was it again? Maybe 150. So that we can see the shape. That's better. Okay, so with this, after you hit the graph button, you can go to analysis, G-solve, and do all of those things. So for example, we can do x-intercept. You can see the x-intercept is -2. And if you hit right, it gives you the other x-intercept. You can also go to analysis, G-solve, and let's go for maximum. It gives us 154, our maximum. We can go analysis, G-solve. Now point inflection is inflection, and it gives us the other point. And then lastly, the y-intercept, G-solve. How would you do it? You go for y-intercept. So 0 and 32. So you can see the CAS is very handy. Make sure you get familiar with all these instructions. So let's catch what we have, the intercepts, stationary points, and local max. So thinking about the stationary points of inflection, -2, and it's a positive graph, so it's going to go positive to positive again. And then the local maximum at 154, so it's going to do like a curve and then go through the 2. Just like that. So remember the steps. First of all, find your x and y intercepts like you've done before. Then find the derivative to find a stationary point, and then put in a table and find the gradient slightly to the left, slightly to the right to see what type of stationary point it is. Thank you for watching and see you next time. Bye!